welcome to our esteemed guest and speakers and convener Dr. P. Nageswara sir, Professor, Head of the Department, and distinguished faculty members and participants from various institutions who have joined us today. I would also like to extend a special welcome to today's speaker, Mr. Avin Dayal from IIT Hyderabad, who is with us today. So next, it's my pleasure to invite Dr. P. Nageshwara sir to deliver his welcome address.
Thank you, Lakshmi. Respected the participants from various institutions and our resource person, Mr. Ravindra Dayal, participants from various other institutions, students, a very good evening to one and all. Our principal sir is supposed to join for inaugural session. I think sir is having an urgent meeting with some other delegates. It's my privilege to welcome all the participants to this 1 week faculty development program on foundations of machine learning and deep learning, concepts, models, applications, scheduled from 9th to 14th September 2024. It is being organized by Department of PC, Vardhaman College of Engineering. So in collaboration with IIT Hyderabad under Prime Minister Research Fellowship. I thank Mr. Ravindra Dayal for accepting our invitation, for being the resource person for this. Of course, nowadays it is become mandatory to know everyone about the machine learning and deep learning. These terms became buzzwords. Of course, we cannot see any field without the help of the machine learning and deep learning. The foundation of machine learning and deep learning revolves around some key concepts such as data-driven algorithms, statistical models, and optimization techniques. But next 1 week, you will be studying in detail about all these concepts. Machine learning focuses mainly on enabling computers to learn patterns from data, while deep learning is a subset of machine learning. It is known to everyone, which uses the neural networks to model complex relationships. Both areas involve models like decision trees, support vector machines, etc. There are a number of applications where use machine learning and deep learning concepts. It may be speech processing or it may be image processing to up to predictive analysis. The era of this machine learning and deep learning definitely transforms industries with intelligent and automated, which gives automated solutions. I hope this program will help the students, participants, and faculty to know more about the machine learning and deep learning concepts and how they are being used in different areas, what are their applications. And of course, practical sessions are also there. That too, these sessions are scheduled from 7 to 8:30, which will not disturb your regular classwork. I'm sure that the participants will get benefited out of this faculty development program. So thank you, Varandal, for registering for this wonderful faculty development program organized by Department of PC. Thank you, Varandal.
Thank you, sir, for your inspiring words and for your continuous support in nurturing the academic environment in the Department of ECE. So now I am privileged to introduce today's speaker, Mr. Avin Dayal. So Avin Dayal is a PhD scholar at Department of Artificial Intelligence, Indian Institute of Technology, Hyderabad, and a proud recipient of the prestigious Prime Minister Research Fellowship. He previously worked as visiting research scholar at the Department of ICT, University of Ager, Norway. He received his bachelor degree in computer science and engineering in 2020. He has published in top AA conferences such as New York IPS and ECCV. His main research interest area in deep learning methods for autonomous ground and aerial vehicles. I welcome Avin Dayal sir to welcome to this FDP, and please address the gathering.
Yeah, thank you, ma'am, and thank you, Professor, for the warm welcome. I hope I'm audible.
Yes, sir.
Yes. So thank you all for joining today's session. I'll quickly share my screen and we can get started with today's session. Yeah, I hope my screen is visible. If someone can confirm, ma'am.
Yes, sir. It is visible, sir.
Yeah, thank you. So, good evening, one and all. Welcome to this 1 week session on foundations of machine learning and deep learning. So, as already previously introduced, I am currently a PhD scholar in the Department of Artificial Intelligence at IIT Hyderabad. And so, this particular course has been designed keeping in mind for people who are completely new to this field and also people who have very limited background and want to learn more about this field. So, keeping that in mind, we have framed this course in such a way that everyone can understand and benefit from it. And also already discussed by the professor, there is also practical sessions, which is very important. So a basic Python programming requirement is needed, but which I'm aware that all of you are aware of Python programming. So given with that, I'll start off with today's session with very simple introduction to what exactly is this field of machine learning, deep learning, where can we use these things, and then I'll also discuss few concepts about what is supervised learning, unsupervised learning. There's something called as reinforcement learning, and also I'll discuss what type of data that you can see in today's world, and then a little bit about metrics on how can you say that one machine learning model is better than the other machine learning model. So you'll get an overview of all the different terms in that are being used in today's world. From next week, from tomorrow onwards till the end of the week, we will be covering various algorithms, classification algorithms, regression algorithms, clustering algorithms, and we'll end the course with introducing to neural networks and state of the art methods like LLMs, diffusion modules. Okay, that being said, let's get started. So the first and basic question that anyone needs to ask, what is machine learning, right? So any guesses? So let's keep this course interactive. You can always drop your answers in the chat. I have two screens so I can see your answers in the chat. So if you can drop, or maybe if you can raise your hands, I'll ask you to unmute. So let's keep it more an interactive session. So any guesses? What do you think machine learning is? What comes to your mind when I say machine learning? Two words, machine and learning. Okay, maybe I'll explain what I mean by that. So as you can see from the image, a machine. Let's imagine that a 2-year-old or 3-year-old kid is given a bunch of different images of fruits and vegetables, and you tell the 2-year-old kid to learn what are the fruits and vegetables given the labels for each of these fruits and vegetables. Like the first one, you tell that this is an apple. Second, you say this is a banana. You keep on telling each, you point to each image and you say this is a particular type of fruit or vegetable. So what are we making the 2-year-old kid learn over here? We are giving them a lot of data and we're asking them to learn a particular pattern. Okay, if you see a particular fruit like shaped like this, it means it's an apple. Or if you see a particular fruit shaped like yellow color and green color on top, it means it's a pineapple. So this type of making the model or making this 2-year-old kid learn patterns from a particular input data is nothing but machine learning. So in more official terms, you can think about machine learning as a branch of artificial intelligence that focuses on building systems that makes decisions based on data. That is the official definition of machine learning. But you can think about machine learning to be nothing but learning patterns when you're given a bunch of data. Okay, so as also discussed by Professor just 2 minutes ago, so this is very important to learn the difference between these three things: artificial intelligence, machine learning, and deep learning. I would suggest this is the first thing you'll always encounter when you go outside and tell someone that you know machine learning. They'll first ask you, what is the difference between these three? So it's very important to learn the difference. Artificial intelligence is the broader and the bigger field where you are trying to create a machine that can mimic natural intelligence or human intelligence. Inside artificial intelligence, because this is not a field that is just started from 2000s, it is a field which is rooted back to 1890s. There's the first time when people actually thought about creating machines or artificial intelligence things, basic and entities. So since that date, people have come up with a bunch of different algorithms and all. And out of all these different algorithms in artificial intelligence, the ones that are most popular in today's time and that is giving the most results is this area called as machine learning. And like I said, machine learning is the area which deals with learning patterns from the data. And then inside machine learning also, there is a subset called as deep learning, which is nothing but it contains neural networks, artificial neural networks. And this deep learning is what is the most famous type of algorithms in today's world, where you hear about large language models like ChatGPT, or you hear about models like Llama models, Lava models, bunch of different models. All of these are belonging into this category called as deep learning. So I hope this distinction is very clear. Please let me know if you have any questions for the same. Okay. I would also request everyone to please mute yourselves. If there's any question only, please unmute and ask. Yeah, thank you. So it's good to know, okay, the differences between these three things, AI, ML, DL. But why should you care? That's the next question which people ask. Why should I care about machine learning? So these are just bunch of different quotes said by great people in today's world, like Bill Gates. Everyone is aware. He was the founder of Microsoft. He said that machine learning, a breakthrough in machine learning, could be worth 10 Microsoft companies. And then there is another person called as Tony Tedder. He's the director of DARPA. DARPA is a US defense organization. They came up with actually the internet concept was created by DARPA. So he said that machine learning is going to be the next internet. And similarly, there's another very famous professor called as Andrew Ng. So he was one of the key proponents of bringing machine learning into everyday curriculum. And he said that machine learning is nothing but today's electricity. So the advancements in machine learning will have huge impacts. In terms of market size, you can see that people have predicted machine learning to go beyond 700 billion US dollars by 2032. This estimate just keeps on increasing every year and year. So it's very important that everyone in today's world at least needs to know what ML DL is and have a basic idea of these workings, so that will be beneficial for your own career. Okay, then let's talk about fine, the machine learning algorithms are there, but we also learn about traditional programming algorithms. I'm very sure that you all are familiar with algorithms such as merge sort algorithm, quick sort algorithm, or your binary search algorithm, a bunch of different classical traditional programming algorithms. So what we need to understand is, how is machine learning different from these traditional programming? So as you can see from the image, in traditional programming, what do? We have our input data. Like for example, you send a input as your array, right? In your C++ or C programming, you know what is an array. Array is nothing but a bunch of numbers, a list of numbers. So that is your input data. Then you have a program with you. Now, what is the program? It could be your merge sort algorithm or quick sort algorithm or searching algorithms. So given your input data and your particular program, the computer then uses these two and gives a particular output. Like in searching algorithm, it will search whether a particular element is present or not in the array. In the sorting algorithm, it will sort that entire array, either ascending order, descending order, whatever you program it to. So that is your standard traditional programming. Now, what do we do in machine learning? In machine learning, we give input your data, and your other input will be output itself. So for example, in that first image of the 2-year-old kid learning, right? The input will be an image of an apple. The output will be the label for that image, which is apple. So you give a pair like this, input output pair, a data and output pair. You give like thousands and thousands of samples, and you make sure your computer learns what is the pattern or the programming that maps this data to the output. So that is the difference between your standard traditional programming and machine learning. I hope this is clear. Okay, moving on. So once you understand this difference, then the next difference you need to learn is what are these bunch of different terms that you listen in today's world. Like you hear about data science, you hear about data mining, you hear about statistics, and there is also implicit learning, inherent learning, a lot of different terms. So most people categorize all these terms as one and the other, but there are obviously slight differences. Like data mining deals with how to collect loads, hundreds and thousands of GBs of data. Data science deals with how do you pre-process or process this data. Machine learning deals with how do you model these data. While there are certain subtle differences, but you can think of all of these terms to be doing nothing but learning the underlying patterns between the input and the output. So it is also good to know that such terms exist. Obviously, these are not the only terms. This list of terms just keeps on increasing in today's world. There's no end to that. Okay. So once you understand the different terms, next is when do you use machine learning? This is a very important question. As an engineer, you need to know when should I actually use machine learning. It is not always necessary for you to actually use machine learning. So many people in today's world are unaware of this fact. I've personally encountered many engineers who don't have to really use machine learning in their particular given task, but they still apply machine learning because that is the hype. So it is very important for people to understand when to even use. So let's list out the certain use cases, or you can say certain scenarios where and how you should apply machine learning. Let's talk about the first scenario. The first scenario says that when human expertise does not exist to solve a particular task. What could be an example? Navigating on Mars. So you all must be aware of NASA's Mars rover, which is a robot which is navigating on Mars and collecting data, sending us information about how the Mars land is, terrain, water and all. So in such scenarios, when human expertise does not exist, machine learning needs to be used, because you then have an algorithm or a machine that can inherently learn from the unexplored areas or unexplored scenarios. So you don't have to have a certain database of particular conditions, or you give a particular yes and right yes or no answer. Instead, you give a machine learning algorithm and you say you only go and learn on your own and navigate through the entire area. So that is one scenario where you have to apply machine learning. The second scenario is when humans are unable to explain their expertise. So one good example is speech recognition. So speech recognition is an area where even the very good experts in today's world are unable to explain every phenomena that happens during speech recognition, because it is very complicated to analyze this entire data of speech. So in those scenarios, you can again apply machine learning to model how the speech recognition can be done. Third scenario is when your solution changes in time. So you must be aware about the routing algorithms in your computer network. All these routers which you use, right, in today's world, like your Wi-Fi routers and all, they all have something called as routing algorithms. It means nothing but that router tells what particular website to route to, or if you're doing some Google search, right, it takes that as an input and then directs you to correct website or correct another router, another hop. So those particular algorithms, they keep on changing over time. Why do they change? It depends on the traffic on your router. Sometimes many people are connected to a certain router. So then the router should, cleverly change its algorithm to accommodate for this traffic. So over there, the scenario is that the solution keeps on changing over a period of time. So in those cases, machine learning is a very good solution. Now, fourth scenario, solutions that needs to be adapted to particular cases. I think the best case is all of you must be using your phones in today's world, and all of you have fingerprint scanners or your retina scanners on your phones. So again, all machine learning algorithms go behind these scanners. Why machine learning can be helpful? Because you can't really have an algorithm for every person in today's world. There are more than 8 billion people, and let's assume 5 billion people have mobile phones. So it's not possible to have 5 billion different algorithms to cater for each person. In those cases, having machine learning is helpful because only one or few algorithms can help you to adapt to different individuals. So scenario 4 is one again such scenario. And final scenario is a very simple scenario, I would say. Whenever you have a lot of data which is easily available, like your internet, right? Like your world wide web. You have a lot of data available for very cheap. And whereas if you want to extract knowledge from this data, it is expensive. Then you apply machine learning. So there is a difference between data and knowledge. Data could be just a bunch of different websites. Knowledge would be what information you're extracting from each of these websites. So there's a subtle difference between them. So when you have abundant and cheap data, again, easily apply machine learning models. Okay. Now let's go to some applications. I wanted to show you some interesting videos, to motivate more about what all are possible in today's world. So let's start off with different areas. So this is the area which I am working on, which is called as autonomous driving, which you all are familiar. Tesla is a very popular company which is trying to achieve self-driving cars. There are also a bunch of different companies. So this is what a typical autonomous vehicle will see when it is driving through the roads. So this is an example of driving a car in US, San Francisco. So as you can see, it sees that what lane it should travel to, which is that green color line. It also sees different objects on its sides. Like you can see what the actual image is from the right, bottom right. But what the algorithm is seeing, it is seeing, okay, a big bounding box for a car, a small bounding box for a human. It also sees far away distances, like all the purples are different types of objects. Yellow is some other type of object in front of it. Now, why it should know all these things? Because it takes all these things into account or into as an input, and then it will make a very wise decision on how to go, whether to go straight or left or right, those information. So let's see a video of it. So as you can see, a bunch of different entities and objects are moving around it. It stops as a red light. And then as soon as it gets the green light, it will move further. Now it got the green light and it moves further. So this is a very simple, I wouldn't say simple example, but this is one very useful application in today's world that uses machine learning. Obviously, there is a lot of in-depth algorithmic knowledge that is needed to develop such systems, but ML is the starting way to understand what these algorithms are made of. Okay, going to another scenario, very important and again upcoming, I wouldn't say upcoming, it's also very established area is applying machine learning knowledge on medical analysis. So you have a bunch of different CT scans of brains on the left side. And if you want to identify whether there is a tumor or whether there is a chance of growing a tumor, you can use machine learning. So this actually helps a lot of people in today's world from dying from early deaths, because previously people didn't have such techniques to identify or forecast whether within 10 years that person might get a particular brain due to some some way or the other the person couldn't survive. But in today's generation, that is not the case. You can easily forecast what the health would be in next few years, and then you take necessary precautions. Even on the right side, you can see the same thing in a 3D plot where you scan the entire brain and then you see what are the potential, is there any tumors that are formed, any lumps or abnormalities that are being formed. Again, thanks to machine learning and deep learning for such type of technology. Now let's go to the most popular in today's world, ChatGPT. I don't think I need to explain what ChatGPT is. Everyone are already using it. So it's a chatbot. A chatbot is nothing but an algorithm that is made to interact with human beings in a very human way. So you can ask it a bunch of questions. Like in this particular example, it is asking it to create a website without any code. So the human just needs to tell what it needs in the website, like what are the different UI features it wants, buttons it wants, and everything. The ChatGPT will instantly write a code and give the website made for it. So this is just one thing. ChatGPT can also write songs, and nowadays you have even voice feature in ChatGPT. You can talk to ChatGPT also. Soon people are saying the video is also going to come out in probably by the end of 2025. So the progress in these GPT type of models are insanely fast. Then there is another very interesting application of robotics. Everyone always, whenever you say AI or artificial intelligence, people immediately think of robots. So this is a very latest robot which was built by Stanford University in 2023, and they called it Mobile Aloha. So let's just see what all it can do. So it can garden your plants, it can clean your house, it can also make your coffee. It is also able to clean what any dirt that is there, do your dishes. It is able to do that. Also, it is able to take things out of your fridge, create your snacks or food. It also plays with your pets, can take out your trash, doing certain laundry. Yeah, so a bunch of different household chores can be done by ML algorithms. Now, I wanted to ask you an interesting question. So, I've shown you all the success that has been done in machine learning and deep learning, right? So, do you think that we've solved the problem of AI, or is there something else that we still need to do? Because as you can see from the video, the robot is able to do almost all of your basic household work, right? Cleaning, dusting, making food, playing with your pets, and everything. So maybe a question that for you audience, do you think AI problem has been solved? Any guesses? You can always unmute and answer. Okay, so the answer is no. The problem of AI is not yet solved because the same robot which we saw showing different success, right? It also comes with a bunch of failures. So, for example, when it is trying to pick up this wine glass, it just completely drops. And yeah, when it is trying to, make the robot should turn the plate, it was not able to turn the plate. Similarly, when it had to do simple navigation, it was not able to do that. Even opening of the door was not possible, where it had to keep simple things. So even like picking up simple objects like pens and all that was not possible. Yeah. So obviously, so that means that basically in there's a lot of scope or a lot of research that is yet to be done to actually make AI more and more efficient. So right now AI is at a very good level, the models that are developed, but it's still at the grassroots level is what many scientists still term it. So and we are still yet to do a lot of research and take it way and way forward and actually what we want to create as an artificial intelligent being. So this is again a simple case where ChatGPT very badly fails. Like for on the left side, if you see, if you ask ChatGPT what is 1 plus 0.9, it says the sum of 1 plus and 0.9 is 1.9. But then if you simply twist the answer and say, isn't it 1.8? Then it doesn't really reason, it doesn't really think much, and it immediately says, oh, yes, you are correct, 1 and 0.9 sum is 1.8, which is not true. Similarly, on the right side, this is a game we all played as a kid, right? When someone says the word, say drink, and it says drink, then you say it 10 times. So it confuses to say the word it instead of it. What we mean is to say the word drink. So this is again erroneous case. So some small simple things which for us humans it is not even a big deal. Even those things are not easily achievable with today's algorithms. Obviously, there is being more research going on, and that's where we need more and more engineers and researchers to come into the play. So I didn't cover all the applications, but you can all. This is again a list of all the popular applications where you can use machine learning. Again, in no way this exhaustive set. You can always Google it, and you'll find bunch more new algorithm application areas. Okay. So I've talked a bunch about motivating why AI is needed, why ML is needed. So let's now get into a little bit more details about machine learning and what are the different settings in machine learning. And then we can talk about the different algorithms and where each algorithm falls under in which setting. Okay, there are two popular settings in machine learning. The first setting is called the supervised learning and the second is called the unsupervised learning. And again, in recent times, a lot of new terms are coming up, but the first two are the most popular terms. So we will only cover the first two learnings in our particular course. The first learning says a supervised learning is nothing but we predict a label y given an input x. So now what do you mean by that? Like in the very first example of the 2-year-old kid learning, what I said, we give an input of a image of a fruit, and the label also we give along with the input image, and the label is either describing the fruit, whether it's an apple or a pineapple or whatever it is. So giving this input x and the label y, input x is nothing but the image, the label y is the tag of that particular fruit. Giving these two together makes the setting a supervised learning, because you're giving a supervision to the algorithm, right? You're telling what is the input actually is, whether it's what type of fruit that particular image actually is. So that supervision is being given, hence it is called a supervised learning. Now let's talk about unsupervised learning. Like the name suggests, it is the opposite of supervised learning, where you only have a bunch of input data, that is images, but you don't have tags or labels associated with each of these input images. Now, how do you learn patterns in this? Is where you, that is the challenge. You basically have bunch of techniques like dimensionality reduction, clustering, where you group search similar input images together, or you maybe project them into higher spaces and lower spaces. We'll discuss those things as we see the algorithms. So there are a bunch of algorithms tackling unsupervised learning. In supervised learning, there is again two different sub settings, I would say. One is called the classification setting, another is called the regression setting. So the difference is very simple. In classification, your label is a discrete value, and in regression, your label is a continuous value. What I mean by discrete is like, for example, if there are a bunch of fruits, each word is a discrete value, like apple is one value, pineapple is one value. Regression is continuous, like the values go from minus infinity to plus infinity. So just take that label y, and you can immediately visually inspect based on the values that it contains, whether it's a classification problem or a regression problem. And then the other settings I'll explain in the coming slides. So this particular difference, I hope it is clear. It is very important. So if you have any questions, please unmute and ask me, because these are very important for all the other coming lectures. Okay. So let's first talk about the classification setting. So how do you even get your data? That is first important thing that you need to ask, because one type of data is the images, but it's not always that you get images as your input. Sometimes your simple Excel sheet, right, which you've been using for so long, that itself is called as a data. That itself can be used as a data. So let's look at the image on the slide. So this simple Excel sheet has 5 columns. The first 4 columns is what we call as attributes or features. So there are a bunch of words for the same thing. So the first 4 columns are called as the features of your input data or attributes of your input data. Then the last column is your label y, which is we have basically class, telling which particular class this particular input belongs to. An input example or a data point is nothing but one row. So let's go again slowly. So your entire data is this Excel sheet. The first 4 columns are called as attributes or features. Each row is called as a input sample or a data point. And the last column is called as the label y. And how many classes are there? 3 classes are there in this label y: Verisocolor, Setosa, and Virginica. Hence, since there are only 3 classes, it's a discrete label y. And that's why this problem is called as classification problem. So I hope this is clear how we deduced what type of a setting this is from the data. First, look at your input attributes or features. Then you look at how many number of rows are there. That is the size of your data, number of samples or data points. Then you look at your label y, which is your last column. And then you see whether that label y is discrete or continuous. And based on that, you can say whether your problem is a supervised classification problem or a supervised regression problem. Okay. So what do we try to achieve with supervised learning with this classification task? What are we trying to achieve? If you can see, this is what exactly we're trying to do. Even if you take any neural network algorithm, right, any LLM for that reason, any large language model, all of them inherently try to do this. It is trying to learn this boundary. If you're taking a two class problem, like we have two classes on the left side, your circles and your crosses, x's. And what you want to do, you need to have or create this green color line that will separate these two classes. That's it. If you have multiple classes, you create this more complex type of a figure with three different classes or classifiers, like green classifier. When I say classifier, it is the straight line. So your green line, red line, and purple line. So you create a more complicated figure. If you have a simple two class, you just have one straight line. So all you try to do in your classification is create such lines to separate the classes from each other. That's it. All your neural networks, all your large language models, it's just how to find this line is what the algorithm tells. Each algorithm has a different approach in finding this line, but underlying all of them try to find this line to separate the classes. That is very important to have an intuition when you're using an algorithm, because that is again something I've personally observed in many people. They just use the algorithm like, oh, they get some data and then they just apply a bunch of algorithms on it and then they report them. But why are you doing it? What is the underlying intuition that is happening behind these algorithms? That is very important, and that is what I want to convey from this 1 week course. Okay, so what are the available classification methods in today's world? So again, these are the popular ones, but with more and more research happening, there are a lot of variations to these algorithms. But these are the most popular classification algorithms. You have your k-nearest neighbors, decision trees, naive Bayes, support vector machines, then logistic regression, neural networks. Neural networks comprises of all your, again, convolution neural networks, large language models. All of them come in these neural networks. Then you have ensemble methods. Don't worry if you don't know all these. We will go one by one with each of the course lecture. Okay. So we saw classification. Now, if you have a data where your last column again is your y, but now if you look at y, this is not discrete anymore. It is any real number value, which is price in this case. So it is any value which can be in decimals also, or in between minus infinity to plus infinity. Hence, this problem is called as a regression problem. You again have your first, whatever columns you have, like 7 columns. These are all your features. In this case, you have 5 rows. So you have 5 data points or samples. And your last column, that is your y, which is continuous. So this problem is called as regression problem. Now, what are we trying to do in regression? Again, like previously, we learned a line which separated the classes. But in regression, we will learn a line that will best represent this data points. So that is what inherently we are trying to learn by any regression model which you use. You are trying to fit, we say fitting a line basically. We are trying to create a line that will fit this data very appropriately or correctly. So how do you say correct or wrong? That we'll see in the next slides. There is something metrics like root mean square error and all those things. Based on those values, you say whether this red line is fitting this data correctly or not. But try to understand what are we trying to do here. Try to create a red line that will fit through this data points, blue color data points. Okay. Then we come to the second setting, unsupervised learning. So like I said, there are multiple techniques in unsupervised learning. And in unsupervised learning, you don't have your label with your input data. You just have your input data. So one popular technique or a very simple intuitive technique is clustering. Clustering, it is very simple. So if you see on your left side, the gray points are your input data. You give it to a clustering algorithm. What it is trying to do, it is just forming different clusters. What is clusters? Clusters is nothing but a group of points. So how does it form these clusters? It basically takes some similarity between the input data. Like some, you can take like cosine similarity. You all are familiar with the basic similarity, cosine similarity, right? If there are two vectors, you can use the cosine formula to get the similarity between the two vectors. So if the value basically goes between -1 to +1. So this is, you can say that based on cosine similarity, it will group all the similar points together and form one cluster. So with this, for this input data, it forms 3 clusters. A very simple type of unsupervised learning algorithm. Now there is also a little bit complicated algorithm called as dimensionality reduction. So for that, what you need to understand is, usually when you get your data, that is in the bottom cube which you see, right? Your data usually has higher dimensions. Again, 3 dimensions is not a lot in real world scenarios. When we deal with data in actual real world data, you get approximately 50,000 to 1 lakh dimensions also, which we can't visualize as human beings, right? So you see a lot of high dimensional data, and the idea over here is, whenever you go from low dimension to high dimension, you create more and more spacing between the data points. So when you go from low to high dimension, or from opposite way also, if you go from higher to lower dimension, you're learning important features that are actually present in your high dimensions. Because all the 3 dimensions might not be important, maybe it is just 1 dimension that is important. So by collapsing these dimensions, you can identify which is that one particular dimension that is the most representative of your data. Dimension is again another word for features and attributes. So like I said, in machine learning in today's world, you have so many different words which all mean the same thing. So you need to be aware of when what a particular word means with the help of context. So when in this case I say dimension, it means it's feature. So there might be initially 3 features, but all the 3 features might not be important. Only one feature might be important, and that you identify by reducing the dimensions of your actual input data. Okay. Then there is this another setting called as reinforcement learning, which you all must have heard about this company called Google DeepMind. So Google DeepMind is a company which was formed in which got very popular in 2014 because of their algorithm called as AlphaGo. So AlphaGo is an algorithm which was able to using which they defeated the world champion in the game called as Go, which is a Chinese game which is very complicated. So that is how reinforcement learning got very much popularity in today's world. They actually showed that with the help of such type of techniques, they were able to defeat the best of the best minds in the world in that game of Go. Obviously, there are a lot of extra help and all they took, but still, this was the first time they were able to defeat a human being at that game, that to a grand champion at that game. So let's look at what reinforcement learning simply means. So reinforcement learning says that, let's say you have a mouse. Now this mouse is left in a maze, that is your environment. Now what is the task for the mouse? It should navigate through the maze, come to this end point, which is the cheese. Now how does a mouse do? It keeps on going into a bunch of different directions, and then it has a memory, right? It also realizes, okay, I went into this path previously, it was a dead end, so I will try a new path. So this constant loop, right, where it takes one step, looks at its memory whether next I should take a right or a left, and then based on its memory it will take a right and left, and then again it will repeat the process until it gets the cheese, until it gets to this cheese. This entire trial and error or the feedback loop is what reinforcement learning is. So reinforcement learning draws its inspiration from control theory from the electronics background. So control theory and reinforcement learning have very much similarity, and people have actually used a lot of control theory algorithms to develop better and better reinforcement learning algorithms. Okay, so but we won't be covering those algorithms because it is way more advanced and out of the scope for this lecture. But it's good to have an idea about such type of interesting setting called reinforcement learning. Okay, so let me quickly pause. I've covered a bunch of different settings with a bunch of different definitions. I hope everything is clear. If you have any doubts or any clarifications that needs to be done, please unmute and ask me. Okay, great. So if everything is clear, now let's try to categorize all these different settings which I talked about into the simple table. So there are 2 settings, like I said, supervised and unsupervised. And we have 2 different types of data: discrete data, continuous data. In supervised learning, based on your label Y, if it's discrete, we call it classification. If your label Y is continuous, we call it regression. Whereas obviously for unsupervised, you don't have labels. It is based on your input data. If your input data looks discrete, it's clustering. If your input data has continuous features, then we use dimensionality reduction techniques. So this is a broad categorization of the popular settings based on its input and or output data. So there are again further different levels of categorization called as inductive learning, transductive learning, online learning, offline learning, generative learning, discriminative. Generative models, right? This generative models is what today's large language models, chat GPT, diffusion models, whatever these popular names you hear, right? All of these are generative models. So there is something called as discriminative models, which are the opposite to generative models. Then there is parametric, non-parametric. So we will keep on, whenever we come across a new algorithm, we will try to categorize them into one of these types so that you'll have an idea about what are these different types of models and when can you categorize a model as generative or discriminative, online or offline. So now that we talked about the settings, now we come to another interesting part of the today's lecture is how do you evaluate these models? Like I said, there are a bunch of different models, right? K-nearest neighbors, logistic regression, and so and so, so and so, so and so, neural networks and all. But how do you say which model is better like than the other? For that, you need something called as a metric or evaluation score. Now, how do you get that evaluation score? That is one factor. And what is the pipeline that you need to follow to actually evaluate between these two models? That is where this particular concept comes as training and testing of machine learning models. So let's first look at this figure. Let's try to go step by step and look at this figure and understand what are we trying to solve over here. So let's assume that we have two classes, cats and dogs. In this universal set, which is the top set, universal set says that I have collected all the images of dogs that are possible in the world and kept it as X's, and I've collected all the images that are possible in the world and kept it as circles. That is the ideal scenario which you have. But obviously it is not possible, so that's why we call it unobserved. We don't see such type of a set because it's not possible to collect all types of dogs and cats images. Now in reality, what do? In reality, you observe a small subset from this universal set, which we call the training set, and on which you apply your algorithms to create these lines to separate these two classes. So this is what you actually observe. Now, okay, this is great. You are trying to create a line that will separate your training set properly. But what will be the problem is when, let's assume, this particular line which you see, this straight line. Now, if I say this straight line is created by model A, and this curved line is created by model B. Now, between this curved line and straight line, which one is better on the test set? On the right side, bottom right, you see a figure. Which line should I pick? Should I pick the curved line as my final model, or should I pick the straight line as my final model? So can anyone take any guess? You can unmute and answer. Which model should I pick?
Second.
The curved line, me?
Yes, sir.
No, the curved line is actually there's both of them are not good basically, because if you look at the curved line, it is also misclassifying a lot more reds, like all 4 reds it's misclassifying over here, and it is misclassifying almost 5 crosses. Whereas the straight line is still doing a bit better, I would say. It is only misclassifying 1 red, and it is misclassifying these 3 crosses. So I would still, out of these two, straight line is a better option than the curve, but both of them are still bad. Relatively, straight line is better. But what logic we used over here, that which model to pick, is what we are going to learn in the next slides. How do you select which particular line to pick when you have only your training data and not your test data? So like I said, we have 2 phases in our machine learning model. We call the training phase and the testing phase. In training phase, your machine learning model learns to recognize patterns and create those straight lines which you saw. In testing phase, you just evaluate this straight lines or the curved lines which you created on this previously unobserved state. Obviously, you can't have something which is unobserved in real world, right? So for that, you actually do a small trick which we will explain. Before that, let's look at the equations. So for people who are interested in more formal introduction to foundations of machine learning, I've actually introduced some equations in the slides. Even for algorithms, I'll try to keep these equations so that if you're interested in looking at the mathematical side, you can always look into it and get back to me. but all of these needs a little bit of more formal mathematical background. So it's beyond the scope of this. I wanted to keep it simple for everyone. So I'll just discuss briefly what this equation mean, but we can always discuss if you have any errors at the end of the session. So the first thing says training error. This E train is nothing but the training error. The training error is the summation on all the training examples which you observe, and you have a function called as error function. Now, error function basically says how good or bad is my prediction to the ground truth value. You have a ground truth value which is yi. This fd of xi is your prediction. So error function says how good or bad is my particular prediction to the ground truth value. So you collect all these errors across all your input training examples, and then you take an average of them, and that will be your training error. Now, ideally what you want is you want that particular f which is doing good on the generalization error. Generalization error says that you calculate the error on all the possible x and y, and whichever is giving the least error on all these possible x and y's, you pick that particular function fd. So that is what we ideally want, but we can't do this because, like I said, you can't cover all the possible x and y's in the universe, which is impossible. So to avoid this problem, people create a small test set from your input training set. So the previously which we saw, right, there is the observed data which we call the training data, that you further divide into two parts, train part and test part, and this test part will act like a pseudo test to actual generalization error, which you see over here. Now the small subset from the train part which you saw, that will act like a pseudo value to this generalization error. So that is what we call the testing error or test error. So to keep it in simple terms, let's look at this flow chart. So you take your data which you have, which you receive some maybe online source or however you collect your data. You split your data into two parts, train part and test part. Now on the top you have the train part, which with your true labels for each of the example in this train part. You build your model, you fit your model, that is basically creating those lines. And then once you finish the training of the model, you then evaluate the trained model on the test data. And then after you evaluate, you just how do you evaluate? You use the ground truth values for the test data, and you say how good or bad my model prediction is, and based on that you report a particular performance value. So how this performance value, I'll explain what it will be, but for now let us assume that this performance is accuracy. That is the most simple value, right? So you're reporting accuracy based on your predictions and your ground truth values on the test data set. So let me quickly pause. I hope this pipeline is clear on how we created this test and train data set and how you're fitting your model on the train. You then take those trained model and evaluate on the test set and report your accuracy or performance metric. Okay, if there are no further questions, let me move ahead. So now we come across something called as underfitting and overfitting when you're training, right? So what does it mean? We'll look into these figures. So like I said, there is something called as train error and test error, which we previously saw. And these lines are nothing but the classifiers or the model. But after training, this is what is being created. Now, obviously, there are certain type of models which will do very bad on your data set. It's not that every model will do good on any data set. There will be models which will do bad on your data set. So if you look at this leftmost figure, this red color point is doing bad on your data set, both on the trained data set and the test data set. So that's why you have high training error and high test error. So such type of scenarios is called as underfitting scenarios, where the model is not at all a good model for your dataset because even the train error is high, even your test error is high. Now let's come to the other extreme of the spectrum called as overfitting. Overfitting happens when your model is creating such complicated lines where your train error is completely low, like almost zero. It means that it is completely learning all the training examples properly. But when you take that same line and evaluate it on the test data set, you're getting very high test error. It means that the model is basically rote learning. Rote learning is nothing but learning by heart. So we usually tell students, right, especially school students, don't just simply learn the answers, try to do a reasoning behind how your answer is coming. Don't by heart your answers. So that is what is a scenario called as overfitting. We tell here what happens is the model is just rote learning or memorizing the training examples, and that is why it gives very low training error. But when you actually test it, like you test the kids in your exam, when you actually test it, your value will be very high, the error value. So it means that the model is actually not learning, it is just memorizing. What do we want to be is this ideal scenario in the middle, which we call the optimal scenario, where you have low training error and at the same time you have low test error. So as you can see, it is a simple parabolic curve, not a very simple straight line, not a very complicated curve on the right. It is a simple parabolic curve. Now this curve will give you low train error and low test error. So again, let me quickly pause. Very important concept. I think anywhere you go and talk about people, this is when your model is not working, people will immediately ask you to check whether your model is overfitting and underfitting. I hope the difference is clear for all these three scenarios. Okay. So then now I said that you since you don't have your test data, you create a small subset from your test data, from your trained data, and call it a test data. That's what the plan was, right? That was your pipeline plan. But turns out that is also not a very good solution. Turns out that when you create a small subset from your original data set, you are actually creating a bias. Now let me talk about that bias. Now, this is a actual way of how do you want to split your data set into. You need to split it in three parts. So what do? You have your original data set that you're collected. You first split it into two parts: trained data set, test data set. Now you further divide the trained data set into two more parts called again as trained data set and validation data set. And then you train your model on this small subset called trained set. After you finish training your model, then you keep on evaluating after every interval on this validation set, and you keep on checking whether whatever you trained is good or not, or do you have to change any values in your model. So or you have to make it more optimal by making it select some other values of the model. So based on all those things you'll do in this loop which you see, and once you figure out all those best values that you can give your model, that module you take and test on your test data set. So here the difference is the test data set is never seen in the intermediate validation, because there are many models which have some values which we call hyperparameters. Those hyperparameters, those should be manually given by your person who's coding them, by the human expert. Obviously, there is no one correct hyperparameter value for a model that will work for all the data sets. So you do a trial and error over there. You try a bunch of different values for the model, and you keep on evaluating them on this validation set and select the best value that is giving the best performance. That value you then finally evaluate on this test data set, and whatever you get the final test value performance, that is what you report in your research or your product. So there is a subtle difference between your previous pipeline and this current pipeline. So this current pipeline is the one which is the best pipeline, at least one of the best pipelines. There are variations to this particular also, which we'll see in the next slides. But this is the simplest pipeline: training, validation, and test set. Now the next question comes: how do I choose my percentage of data sets between training, validation, and test? Like I said, your original data set, you split it into two parts, right? Train and test. How much should be the percentage? Again, the train set will be split into two more parts. How much should be the percentage? So people did a bunch of different experiments, and they identified the good value is usually 70% is your training data set. If you look at this leftmost set, 70% of your original data set is your training, 10% of your original data set is validation, 20% of your original data set is test. Again, this is not the only way possible, but this is the more standard approach which many people use in their research. 70, 10, 20. That is a standard ratio. You can always look into this figure more to identify how the curves, how the accuracy is affected by different size. They did the experiment on two algorithms, decision trees and logistic regression, and they were able to plot this. And the standard value, like I said, 70, 10, 20. Okay. So now there will be one problem which you will face when you're splitting this data set. Now, what is that problem? Like I said, there are two classes. So let's say positive classes and negative classes in your original data set. Again, it is not always the case that the positive classes and negative classes are of equal number. There might be a scenario where more positive classes are present, less negative classes are present. So there is obviously now unevenness, right? Now, when you do a sampling from this uneven data set, obviously training data set will might see more of positive examples than negative examples. Test data set might have more negative examples than positive. Now, in that case, how whatever model you pick to on this training data set, it will never do good on the test data set because it has seen very less examples of negative class. So now the model is not will not learn that negative classes properly, and that is why your accuracy on the test set will always be low. So this is a very common scenario because it is very easily possible for whenever you're collecting data to have this imbalance between classes. So to overcome this, people do something called a stratified sampling. Very simple. What it means is, if let's just say in the original data set 70% is positive, 30% is negative classes. So you make sure that the ratio remains the same in train set, test set, and validation set. So however you're splitting, make sure that the ratio between your classes is always the same in across these three subsets. Then you can make sure that the model which will work better on train and validation will also work better on test set. Okay, maybe a simple question to check your understanding till now. So can I call this validation again like a pseudo test set or not? Is validation set completely different? What are your thoughts? So my question is, since we created, if you look at this figure, we created from the original train set, from the original set, we create three parts: training, validation, test. And I've also explained the importance or the necessity of this validation set. So validation set, based on what you understand, do you think we can call this validation set like a pseudo test set? Any guesses? It's okay if it can be right or wrong. Okay, so yes, we can call validation set like a pseudo test set because when you're doing this evaluation of different model values, right? So technically you're doing testing only, right? Technically you're evaluating them. What you do on test set, you evaluate. So this validation, people also call it like a pseudo test set. It's like a representation of what my actual test data will look like. So that's why we call it a pseudo test set. So apart from the methods which I showed you, there are also two other methods that are popular, which people use to select which model to pick. Model A, model B, which I was saying, right? So what are these? K-fold cross validation and lever knot validation. Let's look at the first one, K-fold validation. So what does K-fold validation say? It first takes your entire data set and it divides into equal number of parts. So in my case, we took this entire data set and we divide into 5 parts. Now in this 5 parts, make sure this data set is not having the test data set. So let me show what I mean. So first you take the original data set, you split your train set and test set. And after that, you split the train set into 5 equal parts. Okay, that is what you see over here. You take the train set and you divide into 5 equal parts. And now at each iteration, you run this basically for 5 iterations since you divide it into 5 blocks. At each iteration, one of this block will act like a validation subset and the remaining 4 blocks will act like a training subset. And then obviously you repeat the training on these 4 subsets, validate on the first. You do that 5 different times. With each time the validation subset is a different block. And then you report the average performance of all these 5 values. And that will be your validation performance. So based on that, you can select which particular model parameter should I choose. So I hope this is clear, very simple. It's just that instead of directly splitting into 70 and 10, you just basically give equal block a fair chance to be a validation. That is what this entire motivation for this particular pipeline. So the extreme case for this is leave one out validation. Extreme case, when I mean extreme cases, when instead of a block you take every sample as a validation sample and remaining all the samples as training sample, that is leave one validation. So that is the extreme case of k-fold validation. Why do we do that? That is useful especially when your data is less. Now you can sometimes it's not always the case that your data is in thousands or 50,000 or lakhs of data. Sometimes you get only like 500 samples. You also get 800 to 1,000 samples. But you want to evaluate your model on this small data set also, right? In those cases, obviously you can't divide 500 into 70% training, 20% testing, 10% validation, because you're showing more and more less samples to the model to actually train. So in that case, the models won't properly learn. So in those scenarios, you use these validation fold, k-fold validation, or that extreme case, right? Leave one out validation. Those are the use cases for these type of pipelines. Okay. Now, I said that all of these in validation, training and test, you do performance evaluation, right? What is that performance evaluation? That is what we're going to discuss right now. So for different scenarios, you have different metrics. For classification, what do we want to achieve? We want to say how often we are classifying something as right and wrong. That is what is a metric that we want. In regression, what do we want? Remember, regression is fitting that line on the data points. We want how close are we, how close is that line with all the data points that are there in that particular space. In clustering, it is not very straightforward because, like I said, there is no labels for clustering. So people have their own interpretations of metrics. So some people say, I want a metric that tells me how well my particular cluster is describing my original data. And there are also different metrics. But for classification and regression, it is more straightforward because you have your labels with them. Now let's look at that. Okay, before going there, we'll talk about accuracy itself. So accuracy is a very simple metric. I'm assuming everyone is familiar with accuracy. Accuracy is how many correct samples, how many correct predictions you're making out of the total predictions that you're making. So it is a percentage value. You divide your correct predictions divided by total predictions into 100, you get a certain percentage. That is a very simple accuracy which you use. But turns out accuracy is again not very useful in especially these cases. What are these cases? The first case is when there is a large imbalance between the classes. Like I said, in real world, it is very possible that you will find a big imbalance between classes, like 97% of the classes that you have are negative. Now, in that case, if I say 98% is my accuracy, it might not be correct, a correct value, because 98% of the accuracy for 97% of negative classes, it means that it is just doing good predictions on negative classes. It might not do good on the positive classes with the same vigor of 98%. So this usage of accuracy in such scenario is not correct, and it is not helpful. And another scenario is when the cost of misclassifying something is very high than the cost of misclassifying something else. So what I mean with that, let's take this medical domain example, like even COVID you can take, right? So the cost that I wrongly classify a person who has COVID as not having COVID is very high. What is the cost? He or she might lose their death or life. They might die. So that is a very high cost. Whereas if I detect wrongly a person who's not having COVID as COVID, it is still less cost because the worst that the person has to go through is a simple medication. So you see, there is a big imbalance between how much cost it is in wrongly misclassifying something. So when you have such scenarios, again, accuracy is not a good metric. There are different metrics that you will have to use. That is what we discuss in the next slide. So what are those metrics? To understand that, let's first talk about a matrix called as the confusion matrix. Based on these confusion matrix, you come up with new metrics that can be used in these two scenarios which I talked about. When there is a lot of imbalance between classes, or when the misclassification costs are very different. Okay, let's first look at the confusion matrix. So what does confusion matrix say? If let's just take a simple two class problem, A and B, or dogs and cats or whatever. So you have this 2 by 2 matrix. On the rows, you have your predicted values into positive and negative classes. On the columns, you have your actual ground truth labels, right, which are positive and negative. So if a ground truth positive is correctly predicted as positive, this entire block is called as true positive. Whereas if your ground truth is negative, but your model is predicting it as positive, you call it as false positive. Why the name false positive? Because it is very indicative, right? You're predicting something falsely. And what are you predicting? Positive, right? So hence the name false positive. Similarly, if you look at this particular cell where your ground truth is positive, but you're predicting as negative. So you have this false negative. Now, on the bottom right cell, where your ground truth is negative and you're also predicting negative, it is called as true negative. This is a simple confusion matrix you form. So there will be a bunch of samples that are true positive, another bunch of samples which are false positive, false negative, and true negative. So once you collect the numbers in these blocks, then you come up with a bunch of different metrics. So focus on the cells which are on the bottom and on the rightmost side. So these are the new metrics that people use. Accuracy is again nothing but true positive plus true negative by the all prediction values. This is the simplest value which you get. But the other ones which are helpful is precision, which you can see on this bottom left cell, and something called as sensitivity or recall, which you can see on this top right. So these two values are more helpful and better to report when you have those two scenarios of imbalance class and misclassification cost is different. So what does precision say? Let's look at it. Precision says true positive divided by true positive plus false positive. It means that if in the positive class, how precisely am I actually predicting it is a all positive classes as positive. So out of all the actual positive classes, how precisely am I capturing or my model is capturing these positive classes? That is what precision says. Whereas if you look at recall or sensitivity, what does it say? True positive divided by true positive plus false negative. It means that out of all my positive predictions, how many are actually correct? How sensitive am I in predicting something as positive? So that is that is why the name sensitivity. So or recall, basically you can call it, because how good am I recalling by my positive class when I'm predicting all the positive classes and how many of them are actually positive. So that is why the terms recall and sensitivity. Precision is how precisely in all the positive classes am I able to capture them correctly. So these are the two new metrics. Please take a look at it once again once I share these slides, because these are very important metrics that will help you actually come up with better models rather than just using accuracy. Okay, I'll again pause for a quick second. Any doubt, any question in these metrics or confusion matrix itself? Okay, great. Let's move on. Now, previously what we saw was for a simple two-class problem, right? And you don't really encounter two classes in real world. You encounter a lot of classes, like easily when we work, right, in research, we encounter classes up to 300,000 classes are also possible in today's world. So for those things, there is something called as confusion matrix for multi-class. It is a little bit more complicated than the previous, but the definitions remain the same of true, positive, false, negative, precision, recall. All of them remain the same. It's just that values now you'll have to combine them more. Like true positive is only one cell. All of them on the first row which are not true positive are false negative. All of them on the first column which are not true positive are false positive. So the values now will need a little bit more addition and averaging out, but the concepts remain the same of precision and recall. Okay, apart from that, there are also more and new metrics apart from precision and recall, where you can have something called as event detection cost. Basically, like each particular class or each particular type of a cost can be some weighted average between these false positive and false negative. But apart from that, F measure is again very popular along with precision and recall. If anything, you have to remember is these three metrics along with accuracy. What are the three metrics? Precision, recall, F1. accuracy anyways that you know. So these four metrics are what people usually report. What is F1? F1 is nothing but a harmonic mean between recall and precision. So it is nothing but like a weighted average, you can consider a weighted average between recall and precision. So that is where F1 measure or F1 score is used. So, I mean, someone can ask, why do I have to use F1 score when I already have recall and precision? So, like I said, your use case will be different when you're using precision. Your use case is different when you're using recall. So, based on that, if your use case has a hybrid setting where both you need to have high recall, high precision, that is where you need to talk about F1 score. So, people usually report all these four metrics. Okay, I think I talked a lot about different settings. So let's look at a simple algorithm to end the session. Very simple algorithm called as k nearest neighbors. And so you'll have an idea about what are all the different things which we talked about, right? How you can easily think in terms of having the k nearest neighbors algorithm. So what does the algorithm say? I'll just quickly describe. So given that you have two simple input features, sweetness on the x-axis, sourness on the y-axis, and then you have all of these input data points. Each of them have their own class. Like these are all this is strawberry, this is raspberry, orange class. All of this based on these particular fruits, you have to basically form like groupings of similarity. This is not clustering. There are labels possible. So if you look at it, it will look something like this. So category B and category A, these are two classes, and these are all the points in this diamond shape. And now you have a new data point which is in this orange color, and you have to assign a class to this data point. How do you assign a class? You assign a class based on whether this class is closest to the class A, or sorry, whether this point is closest to class A or whether this point is closest to class B. Like you can use bunch of different metrics. I'll tell you how to measure the closeness. But for now, let's assume you have a distance metric. So k nearest neighbor says that k is basically how many neighbors you should look at. K closest, right? So if I pick k to be 3, what are the 3 closest neighbors to this orange color point? That is class A. Whereas class B, only 2 are closer. Third one is a bit far. So that is why if you use k in an algorithm, now this orange point is classified as class A. A very simple algorithm. You don't have to involve any math or anything. You just have to calculate the distance between this new point and all the other points and find out what are the 3 closest points and what class is the majority in these 3 closest points. So this is what the simple pipeline of the algorithm is. Before KNN, you have this new data point, and then you calculate, like I said, the distance values between this data point and all the data points in the data list. And then you identify, if your k is 3, identify what are the top 3 closest points and what is the majority class in these 3 closest points. And you assign your new data point to that class. Since it is closest to the category A, you assign this new data point to category 1. So now the question comes, what is this k value? This is where you use that validation, right? Validation set, where I told you that initially you start off k to be 1 or 2. Basically, you can start off k to be 1, 2, 3. For every k is equals to 1 value, you get a accuracy metric using that validation set, accuracy value. Now k is equal to 2, you again evaluate on the validation set and you come up with new accuracy. So like that, you try out for a different k values, and the best validation accuracy, whichever k value is given, you pick that, and then you use finally do it evaluate on the test set, and that is what you report. So this is how you choose your k value using that validation pipeline. You can use any type of validation pipeline. You can either use k-fold validation, or you can use leave or not validation, or you can simply use the first pipeline validation. Now, what happens when k value is too high or too small? That is very important. So one thing again which people usually forget when using these algorithms is, fine, you understood the algorithm, you understood there are these parameters called hyperparameters which a human should give as an input, but you should also have an intuition or interpret what do these values or these hyperparameters even mean. So that is again something I will cover mostly in this course, that it's not just about having an idea about the algorithm, it's also having an intuition about what each of the parameters will do. So let's look at this k value. So if k is too small, it means that your algorithm will be very sensitive to noise points, which is true. Now let's come back to the example itself. Now, if in this new data point, like let's say my category here A has a lot of noisy points, okay, and noisy points are never good. Now, if this new data point is coming and I say K is equals to 1, maybe that noisy, it is very close to the noisy point, which is very right beside this blue point, right? So in that case, my new data point, which actually might be class B, because of this noisy point and K is equals to 1, it is getting classified as class 1. So that is why it is problematic when K is very small. Now, if K is too large, then you include a lot of points from your neighboring classes also. Now, for example, in this case, if I take K is equals to 8, then I'm taking a lot of values from category B, a lot of values from category A, and then you really can't come to a conclusion which is the actual class. So the best value for K is somewhere in between, not too small, not too large. To identify that best value, you can use your validation pipeline. And like I said, you can use a bunch of different metrics for calculating these distances. You can use your L2 norm, which is your Euclidean distance, L1 norm, which is your Manhattan distance. You can also use semantic distances like cosine similarity and a bunch of different similarity distance metrics you can use. Whichever is actual distance metric in math, you can use that. Okay. So this is what I wanted to discuss in today's class, which was an introduction to machine learning and different settings, different evaluations, different pipelines that you will use, and a simple algorithm called KNN algorithm. And these are the different softwares which will be needed to cover the practical part of this course. So don't worry, you don't have to install these libraries. I would just suggest all of you, please create your, you all have a Google account anyways. Just explore what is a Google Colab. So Google Colab has, obviously it's a notebook. If you all are familiar, there's something called as Python notebook. So Google Colab is an online notebook where you can access them using only your browser. Obviously it's internet connection. You don't have to install any libraries on your local system. So it is very helpful for people who don't have good laptops or who can't support good laptops or GPUs for that reason. Always work on Google Colab, because Google Colab will install all these libraries and also gives you GPUs for free. You just have to have a Google account. So these are again a bunch of different libraries. Python 3, which is very important, which will be the foundation for all the coding problems, code implementations. NumPy, it is used mostly to handle the data. So like pre-processing the data and everything, NumPy does it. NumPy, you can think of it like arrays which you create in C, right? You create NumPy arrays in Python, which can do numerical operations. That's why num is like numerical, py is Python. So it's called numerical Python. It can do numerical operations like calculating logs, doing linear algebra calculations. All of them can be done using NumPy. Matplotlib is a library that is useful for visualization, because it's very important to visualize how your data looks like all these things which you see, right? These are all you plotted with the help of Matplotlib. Sorry. Yeah. And then there's something called as pandas. Pandas is used to handle data which are in the form of your Excel type of data. So we call those as CSV data. Don't worry if you don't know what CSV is. You just think your Excel data, right? Excel data is usually loaded into Python with the help of pandas library. So once you load that, you can do a bunch of operations like filtering columns, filtering rows, appending columns, appending rows, deleting columns. All those things you can do with pandas. Scikit-learn is very important library. Before next class, if it's possible, I would suggest everyone to Google Scikit-learn and understand what it means. So Scikit-learn is where you have all your algorithms of machine learning, your logistic regressions, SVM, decision tree. Except for neural networks. Neural networks, you'll have a different library. Except for neural networks, everything else is available on Scikit-learn, all machine learning algorithms. So the beauty or the benefit of Scikit-learn is you can literally write all your algorithms in 3 lines, 2 to 3 lines maximum. So that is why in today's world, it's not that coding is a big challenge. It's about understanding the algorithms and having that intuition of what these algorithms are doing. That is very much needed, because it's just 3 lines of code and you can implement most of the complicated machine learning algorithms with the help of Scikit-learn. But how do you use the right algorithm is what we want more and more people to learn. Then there is Seaborn. Seaborn is another another visualization software. So yeah, these are the bunch of different softwares. So thank you all. This is what I wanted to discuss in the first session. Hope it was motivating enough for you to continue. And please let me know if you have any questions, anything that you want to discuss. We can discuss it right now.
Dear participants, we would like to open the floor for any questions. So if you have any queries or thoughts you had like to share.
Maybe I also want to add another point, ma'am. I hope the speed and the pace was okay. Like, if you want more mathematics involved, please let me know. Or if you want algorithmic level of understanding with less mathematics, also that is also possible. So I want to cater to the audience. So please do let me know if that is also something which you want to have more mathematical equations and all.
Or else you can type your queries in chat box also.
We require more mathematical kind of things, so that we can understand more.
Yeah, sure. So I'll make sure that the algorithms when we're discussing, I'll always add more and more math components to that. I just won't discuss it on the intuition level then. Yeah, thank you for that.
Thank you, sir. On behalf of everyone present, I would like to extend deepest gratitude for delivering such a comprehensive and insightful talk on the foundations of machine learning and deep learning, sir. We truly appreciate the time and efforts you took to share your expertise with us today. Thank you once again for your valuable contribution to this faculty development program.
Thank you. Thank you all.